I've been alluding to formal charge for a while. We need a way to evaluate what is a good Lewis structure and what is a better Lewis structure. We do know how to check a Lewis structure. We know that there's some non-negotiable rules. We know that a Lewis structure has to have the correct total number of electrons in it that's equal to the sum of all the valence electrons of the atoms in the overall molecule. So we know that's true. We also expect that we should have octets on every atom. Duets, of course, if it's hydrogen or helium or lithium or beryllium, but generally we're talking about 8 or 2 electrons around each atom. That's another important thing. But we have a couple exceptions to that. We've talked about boron having less than an octet. We've talked about some of the period 3 and higher elements having more than an octet. So how do we decide, well, which one is the best option? And that's where we're going to use formal charge. When we move electrons around in the molecule, when we move a lone pair and make a double bond, that's going to end up changing some of the charges within the structure. The formal charge of an element in a compound is the valence of that atom, which we know from looking up on the periodic table what group it's in, minus the number of assigned electrons within the Lewis structure. And we'll count those assigned electrons by every dot in a lone pair, or using a lone pair counts as 2 assigned electrons, but we only will count one of the bonded electrons as being an assigned electron. The idea is that if there's a covalent bond that's representing 2 electrons, but when we're assigning them to a particular atom, one goes to each of the atoms that are in the bond. If I find a Lewis structure with the lowest formal charges, ideally no formal charges at all, they're the most stable. So a Lewis structure with 0 formal charges would be the most stable. One with a +1 charge in one area and a -1 charge in another area would be pretty stable. One with a +2 charge and 2 -1 charge would be less stable, etc., etc. We're going for the fewest charges, and if it has a charge, the lowest value of charge. So like only a charge of a 1 rather than like a 2 or a 3. Additionally, if I have 2 Lewis structures and they both have the same formal charges, so maybe both of them have a +1 charge on one atom and a -1 charge on another atom, having the negative charge on the most electronegative atom is the most stable. So all of these are sort of feel very vague and complex, but they'll come out easier when we practice finding formal charge. So here's an example. This is HCNO. And what I'm going to do for each one, I'm going to look at what the valence is, and then I'm going to check out the assigned. So this is the structure we're evaluating. I might be able to draw a different structure for this, but this is the one we're evaluating. So I begin with the hydrogen. Hydrogen has 1 valence because it's in group 1. In this particular picture, it has 1 bond and no lone pairs. And again, for a bond, we are only going to count one of the electrons as being an assigned electron. So that is 1. So 1, this valence, minus the assigned electrons of 1 is 0. So there's no formal charge on that hydrogen. Now I move to the carbon. It has a valence of 4 because it's in group 14. When I look here, I see 1, 2, 3, 4 bonds it's participating in, and it's assigned 1 electron for each of those bonds. So 4. There are no lone pairs. So now I have a valence of 4 minus an assigned electrons of 4 is 0. So there's no formal charge on this carbon. But when I move to nitrogen, it's in group 15, so it has a valence of 5, but currently it participates in 4 bonds, 1, 2, 3, 4. So it's only assigned 4 electrons. It doesn't have any lone pairs, so I only have those. So 5 minus 4 is a +1. So there is a positive formal charge on this nitrogen atom within this Lewis structure. When I look at oxygen, oxygen is in group 16. It has a valence of 6. Right now I see 3 lone pairs, so that's 2 electrons each, 1, 2, 3, 4, 5, 6, for 6 in terms of lone pairs, and it has 1 assigned electron from this bond. So a total of 7. 6 minus 7 is -1. So this oxygen has a negative charge, formal charge on it. Note that the positive and the negative cancel out, so overall this molecule has no charge overall, but it has charges within it. That's what we're referring to as these formal charges. Now, in this case, we've drawn 3 different resonance structures for the thiocyanate ion. Now, because this is an ion, I expect overall it's going to have a -1 charge. And when I assign my electrons, so I have a valence of 6 minus 1, 2, 3, 4, 5, 6 assigned electrons. So there's a 0 charge here. We do the same for the carbon, 4 valence minus 1, 2, 3, 4 assigned electron is 0. The nitrogen has a valence of 5 minus 1, 2, 3, 4, 5, 6, -1. So this has a -1 charge here on the nitrogen. In this particular case, we can work through these Lewis charges, and you can spend your time doing that. You can pause it if you like. The sulfur has a positive formal charge, and the nitrogen has a -2 formal charge. Notice that a 1 and a -2 equals overall a -1, which is what I'm expecting because this is thiocyanate ion with a -1 charge. Over here, I have a sulfur with a -1 charge on the sulfur and no formal charge on anything else. So when I look at these 3, I'm immediately ruling this one out because this is not the lowest formal charges. This has a -2 and a +1. I'm much better off having 1 formal charge of just 1. So the left and the right are good. But they both have equivalent formal charges. They both have a formal charge of -1 on just one of the atoms. In this case, it's on a nitrogen. In this case, it's on a sulfur. This is where we use the electronegativity rule. We would go look up the electronegativity of nitrogen and sulfur, and we see that nitrogen's electronegativity is higher than that of sulfur. If the formal charge is negative and it's on the more electronegative atom, that is a preferred structure. So this would be my preferred Lewis structure out of these 3, the one with the nitrogen having the formal charge of a -1. I hope that helps clear up how this is going to work. We have, in the last episode, we drew 8 different resonance structures for xenon trioxide. Now we're going to evaluate the formal charge on all 8 of those to try to identify which structure or structures are the most appropriate, the most stable according to the formal charges.